stereo. Now, let's look at the concept of R and S configuration. So we're going to look R and S configuration in organic molecules or in organic molecules. So there are two things that are very important when we're looking at the R and S configuration, and therefore we are going to look the type of bonds which are normally used. One of them is wedge and one of them is the dash. So normally in R and S configuration you will find these two types of bonds. So this is our wedge and this is our dash. So what's the difference between the two? When we have an atom on the wedge, it means that that atom is in front of us. It means that its direction is towards the viewer. So it's coming towards me from the plane or from the page. While when it is dashed like this, it means that it is at the back. That atom is at the back, away from me, the viewer, and meaning that it's going into the plane. In R and S configuration, we have to apply a rule called Can. So there's a guy called Can-Ingold Prelog rule. So this is the rule that we are going to apply to help us assign a molecule R and S configuration. So what does this rule say? The rule simply says that the first substituent attached to the central or attached to the chiral center is assigned a priority from number 1 to number 4 from number 1 to number 4. And this is based on the atomic number. So for example, if I have this carbon here and I have 4 substituents attached to it, let's say substituent number 1, R1, R2, R3, R4. So if these are the 4 substituents in a carbon, then I'm going to list them or to give them priority based on their atomic number. The largest the atomic number, the first priority it gets. And remember, these are atoms which are directly attached to this carbon, and this carbon should be a chiral carbon. We have done what is a chiral carbon, and now we know that it's a carbon which is attached to 4 different substituents. So there are rules that there are sub-minor explanations under Can-Ingold Prelog rule. And the first one, we have said that the atoms directly attached to the chiral centers gets first priority. So for example, if I have this is my bromine, so this is our chiral center, all right, this is our hydrogen here. So these carbons here, or these atoms, in this case you have this carbon, and you have these atoms and this atom here. So these are the atoms which are given first priority. I cannot go to this carbon here before I consider this carbon, because this carbon is not directly attached to the chiral carbon. So these are the carbons that I'll give first priority, including these other atoms. Now, sometimes it happens that now, in this case, for example, let me increase another carbon here. So if you look at this chiral center, these 2 carbons are also attached to another carbon. So it reaches a point in which whereby these 2 carbons are the same. These have 2 protons, these have 2 protons. So what do? We go next to the other carbon which is directly attached to the ones. And then in that case, to help us look which one is going to get the highest priority. So for example, now if I put chlorine here, so if we check, this carbon is directly bonded to carbon, chlorine, and 1 hydrogen and 1 hydrogen. While if you look at this carbon here, it is directly bonded to hydrogen and another hydrogen, and it is bonded to another carbon here. So you have carbon, hydrogen, hydrogen. So in this case, this one will take our second priority because bromine is greater than these 2 carbons. So this one will have our first priority, and then this side will have our second priority, and then this side will have this third priority, and hydrogen is going to have the least priority. Most of the time hydrogen has the least priority, number 4. Sometimes you find that you can have carbon which is doubly bonded to carbon. It simply means that this carbon is bonded to two different carbons. Even if it is carbon oxygen, it simply means that this is a carbon bonded to oxygen and another oxygen. And if you have a triple bond, it simply means that this carbon here is bonded to three different carbons. So those other carbons that we don't see, we call them the ghost carbons or the ghost bonds. So that's some of the things that you need to consider. For example, if this is my stereochiral carbon and this is my bromine, this is hydrogen, and then in this carbon here, too, and then let's put the hydrogen. So this bromine here is going to be our first priority because bromine atomic number is larger than this carbon. And then if you look at this carbon and this carbon, this one is simply bonded to hydrogen and another hydrogen and another hydrogen, while in this carbon, because it is a double bond, so it's bonded to one carbon and another carbon and this hydrogen. So this one is going to take our second priority, and this is going to be third priority, and this is going to be our fourth priority. So that's what it simply means. So now let's apply this now to assign R and S configuration. In normal situation, then when we go clockwise, this we get our R, and when we go anti-clockwise, we get our S configuration. So this is our S configuration in a normal scenario. But so let's look in this example. So let's call this our A. So it means our B we can have still on the same side. So our bromine can now be on the wedge, on the dash, and this one can still be on, OH can on the dash. And then when we look, so this is our B, and when we have C, we can still have them. So we can maintain our bromine here on the wedge, bromine, and then we put this one on the dash, and then our D here we can put it. So this is R, then we can maintain this to be our ash or dash, so bromine, and then because this one, then we can change it into OH. So these are, so we have this molecule. So let's see what are the possible stereoisomers that we can have in this case. How many of them that we can have? So now we need to assign A, R and S configuration in this case. Remember, we have said that when we move clockwise, that is our R, and when we move anti-clockwise, that is our S. However, this can differ depending on the arrangement of the atoms. So now if you look carefully in our A, so this is our carbon number. Let's call 1, 2, 3, 4. In carbon number 4, let's start with carbon number 4. In carbon number 4, our bromine, it is in front. So it means that our hydrogen, it is going to be at the back. So an hydrogen is given priority number 4. So if you look right now, bromine, the atoms which are directly attached to this chiral carbon, so carbon number 4 is the chiral carbon, and therefore our first chiral carbon, and bromine is given the first priority, so this is our number 1. And if then we look at this carbon and this carbon, so if you look here, we have 3 hydrogens. Here we have 3 hydrogens, and this carbon, it is directly attached to this carbon, so we have carbon and 2 hydrogen, and therefore this is going to be our second priority, and this is going to be our third priority. And remember, our bromine, which is our first priority, it is in the front and hydrogen is in the back. So it is very easy in this case, we can move clockwise and giving carbon number 4 and R configuration. Let's look at carbon number 2. Carbon number 2, still oxygen, OH is in the front, and therefore our hydrogen, which is the least priority, it is at the back. So let's look oxygen, carbon, and carbon. Which one is the highest priority? It is oxygen. So this is going to be our priority number 1. And then if we look at this carbon here, it is directly attached to carbon, so it's going to be carbon priority number 2. and this is going to be priority number 3. And because our oxygen, our first priority is in front and hydrogen is at the back, so we can move easily anti-clockwise, and this is going to give us an S configuration. Now let's look at B. So if we look at B, still this is our carbon number 1, 2, 3, 4, and 5. So now one important thing that you need to know is, look what is given. So in this diagram, bromine, it is at the back, and therefore our hydrogen will be in front. So our hydrogen, which is priority number 4, will be in front. So let's look. This is our chiral carbon number 4. So bromine is number 1. And if you look, carbon number 3, it's as high priority compared to carbon number 5, because this carbon is directly attached to this carbon number 2. So we have carbon, and here we have hydrogen, so carbon, hydrogen, and this is only hydrogen. So this is going to be our number 2, and this is going to be our number 3. So we have number 1, number 2, and number 3. So we need to move this way, all right, in the R configuration. However, hydrogen, which is priority number 4, it is in the front, so it is blocking us to view the molecule directly, and therefore we need to change our direction so that we can view the molecule in the right way, and therefore we are going to move this way, and making this one, instead of R, is going to be S configuration, because carbon number 4, sorry, priority number 4, it should be at the back, but it is in front, so it is blocking us to go in the right direction. Therefore we have to turn. Let's look at carbon number 2. Carbon number 2 is also chiral carbon, and therefore oxygen here is still going to be our first priority, and making this carbon here to be our second priority, and this our third priority. And in that case, we have our hydrogen, which is the fourth priority. It is also in front. So now, if this is number 1, number 2, number 3, so we need to come this way. We need to come this way so that we move in the S direction. So we need to move in the S direction. But when we reach at carbon number 3, hydrogen, which is supposed to be which is the least priority, it is in the front, it is blocking us to view the molecule directly. So we need to change our route, and therefore instead of becoming S, we are going to have our R. So in B now we have our S and R configuration, and in our A we have R and S configuration. Let's look what is happening in C. In C, still 1, 2, 3, 4, 5. So let's start with carbon number 4, because bromine, it is in the wedge, meaning that is in front, and therefore our hydrogen, it is at the back. And if we look at priority, bromine will take the first priority. Of course, now carbon number 3 will take the second priority, and carbon number 5 will take the third priority, and hydrogen will take the fourth priority. And hydrogen, it is at the back, so it's much easier to move this way, and therefore carbon number 4, we are going to have R configuration. But let's look at carbon number 2, which is our chiral center here, chiral carbon. Hydroxyl group, or OH, it is at the back, meaning that our hydrogen is going to be in front, and it is the priority number 4. So this one is priority number 1, this one is priority number 2, and this is priority number 3. So we need to move in number 1, 2, 3. All right, we need to move in the S direction. However, when we reach at carbon number 3, the carbon number 4, priority number 4, which is in the front, it should be at the back. All right, so meaning that we are viewing the molecule in a wrong direction. We need to put it in the right direction, and therefore we are going to change this way so that we can have our R configuration, and therefore here we're going to have R configuration. Let's look at carbon molecule D. So we have 1, 2, 3, 4, and 5. Once again, if you look at our carbon number 4, which is our chiral center, we have bromine at the back, so meaning that we are going to have our hydrogen in front. And therefore, actually, if you look at D, automatically it will going to be the opposite of C, which is going to be SS. But let's prove it. Let's prove it if D is going to give us SS. So now, bromine here is priority number 1. And of course, this one will be priority number 2. And this is going to be priority number 3. All right. So in this case, we need to move this way so that it gives us R configuration. But you realize that hydrogen, it is in front, and therefore meaning that we are viewing the molecule in the wrong direction. So we need to take the other route. So we need to move in the other direction so that we can view the molecule in the right way. And therefore, if we change, it's going to give us S. Let's look at carbon number 2. Carbon number 2, the OH group is in the front, and therefore our hydrogen is going to be at the back. And based on the alignment, OH will take first priority, and this one, carbon number 3, will take the second priority because it is directly attached to this carbon number 4, so that is carbon, and then it is also attached to 2 hydrogens, so that is H, while this one is only attached to 3 Hs. So carbon number 2 will have the second priority, this is third priority, and hydrogen, of course, it is the fourth priority, and therefore we can simply move into S direction, giving us SS. So with this one, with just like I've said, D is the opposite of C, is give us SS. So now, how many do we have? We have now, so in C, so let's just write them properly. So C, so this was A, this is C, this is B, this is C. So C we have R, and D we have SS. So let's look at them properly. So we are seeing that the maximum stereoisomers that you can have here are 4. Okay, there are 4. Let's prove. Let's take how in each molecule, either A, B, C, or D, there are two chiral centers, right? There are 2 chiral centers. So if there are 2 chiral centers, remember we said 2n give us the maximum number of stereoisomers, and n represent the number of chiral carbons. In each molecule, you have seen that any molecule we take, their n is equal to 2. So meaning when we have 2 to the power n is equal to 4, and therefore the maximum number of stereoisomers that you can get is 4. So let's list them. So that one can mean that you can have RR, and then we can have SS. Let me just put them properly here. So we can have R, and we can have RS, we can have SS, and we can have SR. So if you look RR, that is the configuration that is for C, RS, which is the for A, SS is D, and SR is B. So now if you look this molecule directly, then we can have now what we call enantiomers and diastereomers. So if you look R and R, so we're gonna have A, B, C, and D. So our RR is our C, so this is C. Let me use another ink, so this is C. SS is D, RS is A, and SR is B. SR is B. So now, just like we have said that stereoisomers are molecules with the same molecular formula but different attachment of the atoms in their 3 dimensions. So with the stereoisomers, we can get, with the stereoisomers, if this is stereoisomers, we can get enantiomers, and we can get diastereoisomers. So now if you look A and B, so we have A, B, C, and D. So if you look molecule A, which is R, if you look C, R and D, S and S. So I want you to pay more attention. If you look at molecule A and B, molecule A and B, this one, the first one that we had here, you see the chiral center is changing from R to S and also S changing to R. If you look C and D, you can also realize that our chiral center changes from R to S and it is also changing from R to S. When a chiral carbon changes from one configuration to another, it's become enantiomers. So we can say that C and D are enantiomers. Enantiomers. And also A and B are also enantiomers. Remember, we have said for enantiomers, the two chiral carbons has to change. For example, take A, it changes from R to S, and in the same carbon number 2, it changes from S to R. So those are enantiomers. When those are enantiomers, then it means A and C then, so we're going to have A and C. We can have B and D, and we can have A and D, and then we can also have C and B. All of them are called diastereomers. Why do we say diastereomers? So I want you guys to look carefully. Now I have redrawn our molecules that we have. Now we are saying that why will we say C and D are enantiomers? We have said if you look C and D, they are enantiomers because now carbon number 4 is changing. The chiral carbon is changing from R to S, and in carbon number 2 in the same C, it changes from R to S. When two chiral carbons changes completely their configuration, then it's become enantiomers. Just like in A and B. If you look A and B, carbon number 4 changes from R in A to S in B, and carbon number 2 changes from S in A to R in B. So that's our enantiomers. And then we are saying that diastereomers are molecules in which if you have two chiral carbons in two different molecules, only one is going to change while the other does not change. For example, we are saying that A and C are diastereomers. If you look carbon number 4 in A, it is R, and in C, it is also R. But if you look carbon number 2 in A, it is S, while in carbon number 2 in C, it is R. So it is only carbon number 2 in both A and B which has changed, in A and C which has changed, but carbon number 4 has maintained its configuration, and therefore A and C are diastereomers. Now, if you look B and D, we are also saying that B and D are diastereomers because if you look in carbon number 4, we have S configuration in B, and in D we also have S in carbon number 4. So carbon number 4 configuration or stereochemistry has not changed. But if you look in carbon number 2, it has changed in B from R to carbon number 2, which is S in D. So that one, it has changed. So because only one chiral carbon has changed while the other has not changed, then it does not qualify to be enantiomer, but it is diastereomers. So also you can look C and B. You can look C and B. If you look C and B, carbon number 4 is S in B and it is R in C, so meaning that that one has changed, but carbon number 2 is R in C and it is R in B, so meaning that it has not changed. Look at also A and D. Let's look carbon number 4. So carbon number 4 is R in A and it is S in D. So there's a change of configuration. While carbon number 2 is S in A and it is S in D. So that one has not changed. So making those ones are diastereomers. So that's sometimes how you can identify enantiomers and diastereomers, and also how you can give them RS configuration. Thank you so much for watching. Hey, remember to subscribe and turn on the notification bell so that each and every time we make new uploads, you get the first person to be notified.